probability distributions yesterday, and we talked about how the expected value is like your mean on those. Today we are talking about one specific type of probability distribution. It's the binomial distribution. This is set up where you have a fixed number of trials, and there are only two possible outcomes. And we've actually done a lot of these, we just didn't call them that. But if you are going to flip a coin 5 times and count how many heads you got, I have a set number of trials, I'm doing it 5 times. There are 2 outcomes, heads or tails, okay? When, I'm trying to think back some of those questions we've had, like we had that question with tires, and some were damaged and some were damage free. I was selecting 2 tires, so there were 2 trials, first and second, 2 outcomes. Your tire was damaged or it wasn't. So we've actually done this a lot, we just didn't call it that. The one thing that's key on this, those trials have to be independent. So if I'm just picking the 2 tires out, those aren't truly independent. But if I looked at a tire, put it back, and then looked at it again, they would be independent. When I flip a coin, what I flipped the first time does not change what I flip the next time. So those are independent. When we look at it, 2 outcomes, success or failure, you can be talking about something with more than 2 possible outcomes. Like if I'm rolling a dice, how many outcomes are there? 6. But if I'm going to say it's binomial, we can only have 2, so maybe I want to roll a 3. So a 3 would be a success, not a 3 is a failure. So 2 outcomes in that respect. And the probability of success has to be the same every time. When you flip a coin, is it the same probability of getting heads every time you flip? Mm-hmm. Yes. When I roll a dice, do I have the same probability of rolling a 3 every time I roll? Mm-hmm. Yes. So that would be a binomial. So let's decide, first of all, if each of these are binomial or not. So the first one, a player rolls a pair of die 10 times. The number of 7s rolled is recorded. So do we have a fixed number of trials? Yep. Yes, 10 trials. Do we have 2 possible outcomes, success and failure?
7s and not 7s.
Mm-hmm. So typically in this we call P our success and Q is failure. So our P would be a 7. What's the probability of getting a 7?
We'd have to list them out, wouldn't we?
Well, just when I roll 1 time. What's the probability?
Oh,
Mm-hmm.
wait, why is that?
Oh, I guess I should have changed this question.
So it should be like a 6.
Yeah, we can't really, let's not even worry about P and Q. But do we have, P would be a 7, rolling 7s, and Q would be not, right? Success is 7s, not, it was failure. So this is binomial. B, an official with the FAA randomly selects airline flights until she finds 10 that were not on time. The number of flights that needs to be selected is recorded. Okay, if it's binomial, there's a set number of outcomes, or a set number of trials. I am looking until I find 10 that were not on time.
Not set.
That's not set, because it could be my first 10, or it could take me 100 flights to get there. So this one is not, because we have not a fixed number of trials. Okay? In a class of 30 students, 55% are female. The instructor randomly selects 4 students. The number of females selected is recorded. So, if I'm looking at this, would there be a fixed number of trials?
4.
Yeah, I have 30 to choose from, I'm going to select 4, okay? So, we're selecting female, so success would be selecting a female, failure would be selecting a male in this case. But here's the problem. If I select a female to come up, so if I say McKenna, come up, and then when I go to select my next female,
It's not independent.
they're not independent, because once I select the first female, doesn't the probability change for the next one? Because I no longer have as many to choose from. So this one is no, because they're not independent. the probability of each of you getting selected changes after I pick someone. All right. Let's look at an example. And I'm going to change this. I'm going to say 3 instead of 4. The 11 largest air carriers had an on-time percentage of 79% in May 2008. Suppose that 3 flights are randomly selected from May of 2008 and the number of on-time flights is recorded. Construct a probability distribution for X using a tree diagram. Okay, so we're just kind of drawing a visual of what could happen here. So for my first flight, all right, I'm selecting 3. What am I trying to decide?
On time or late?
On time or late? So success or failure? Bless you. So you can call them all time or late. I'm just going to use the binomial language, success or failure. Okay, that's my first flight. So when I look at my first one, there's only 2 options. Now my second flight, we would have to branch off each of these, right? So each of those could be success or failure. That's our second one. Then we have a third flight. So from each of these we branch off to success or failure again. So how many total do we have at the end? 8. Okay, so we've essentially found 8 different combinations that we could have arrived on with our 3 flights that we selected. So if I were thinking about this as a binomial, N, how many trials did we have? 3 trials. P, the probability of success. Here, a success is on time. The probability of being on time, 0.79. Q is not on time. And how do we get that?
1
minus P, because there's only 2 options.
That's our P's and Q's, our success or failure.
Yeah, P is just the probability of a success. All right. So if we think about this, X is the number of on-time, let's see, it said X was the number of on-time flights. So we could have 0, 1, 2, or 3. So if we wanted to figure out these probabilities, how many different ways could we have no flights on time?
1.
If none of them are on time, then that means we had failure, 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 right? What's the probability of a failure?
0.2.
So the first one was late, which is a 21% chance. The second one is late, and the third one is late. So that's 0.21 to the third. Okay. If I wanted 1 flight on time, so we need to count how many of these options would have 1 flight on time. So we could have late, on time, late. We could have late, late, on time. If the first one's on time, the next 2 would have to be late, right? So would you guys agree that 3 of my 8 possible options had 1 flight on time? Okay. So if I were trying to find those probabilities, there's 3 of them. And in all of those, 1 flight was on time. What's the probability of being on time?
Wait, why is that third F highlighted?
Because I was saying you could be late, on time, then late.
Oh, for 1 success, sorry. Yes,
All right, so in each of these, matter what order we multiply numbers in? No. So in all these we have 3 different options where it happens, 1 on time, and 2 of them are late. So if I wanted 2 flights on time, could be the first one's late, but then the next 2 would have to be on time. Or first and second are on time and the last one is late. Or first one's on time, second one late, last one on time. So again, we have 3 options where this happens. Right, we have 2 on time, so the 0.79 happened twice, and we only had 1 late. So that's the 0.21. Does everyone see where I'm getting my numbers? Mm-hmm. The final option happens only 1 time. 3 flights on time happens once, so there's only 1 of them. If they're all on time, there's a 79% chance of being on time. That happened all 3 times. So 0.79 to the third gives me 0.493039. Okay. We just found all the probabilities in a binomial distribution. Now, I wanted to show you this to kind of explain where things are coming from. There is a shortcut. If it meets the binomial requirements, there is a formula for how to find it. We need to know how many different times we could get a certain outcome. So like the first one only happened once, the next 2 happened 3, the last one happened once. That is a feature on our calculator. It's an NCF, so I'll show you how to get into that. Then we had P, the probability of success. So in the first one, we had none on time, 1 on time, 2 on time, 3 on time. So your probability of success to the x power, how many of them we wanted. And then our Q, 1 minus P, and we count how many failures. First one had 3, 2, 1, 0. So this is the formula that we will use. And that is how we can calculate the probability for a binomial without going through everything. N is how many trials we're talking about. X is how many successes we want. So I want to show you how to use this, and then I also want to show you how some shortcut options that we have. So according to Experian Automotive, 35% of all car-owning households have 3 or more cars. In a random sample of 20 car-owning households, part A, what's the probability that exactly 5 have 3 or more cars? So in this case, what is N? How many trials? 20. We're talking about having 3 or more cars. What is the probability that we have 3 or more cars? 0.35. Okay. So if we wanted to do this using the formula, we have N trials, C, X. How many successes do we want? That is the
we want 5.
5, the number that we have. P, so 0.35. If I have 5 with 3 or more cars, then I have 5 successes, so 0.35 to the 5th. Then we do 1 minus P. So 1 minus 0.35.
6.5 or 0.65.
We had 20. 5 of them had 3 or more cars, so 20 minus 5 means 15 did not. Okay. Does everyone understand where I got all my numbers here?
Where did get X5, look for C5. I think I got it.
do this whole thing on our calculator. So I'm going to start with parentheses. I'm going to do 20. And then if you go to math, over to probability. The third one down is NCR. So math, probability, number 3. I think on your calculators it'll say 20 NCR. Mine shows this. But then we put in the 5. And then I'm going to close that parenthesis. And then we have 0.35 to the 5th. 0.65 to the 20th. Or 15th. We have 5 successes, 15 failures. And so we get point. Point 1272. Did everyone get that? I want you to flip to the back of your formula sheet, the last 2 pages. I think I did this one or something. Okay. So, if you read at the top, this is the binomial probability distribution. Some of them are on here. This table is limited. It doesn't have every possible combination. But you'll see out in the far left column, it has our n's. Then it has a column for x's, our probabilities, and so forth. Now, we have to be able to do it by hand because if I gave you like a 12% probability, is that across the top? No. But if we have a combination that's on here, we can use it. So if I said my n was 20, so if I'm looking here, this table has 1 through 12, and the back side has 15 and 20. So if we went to 20, and how many successes were we finding? X was 5. And what was the probability of a success? P was 0.35. So if you do the 20 down to 5 over to the 0.35 column, you see 0.1272.
Hey, we got it.
So we can read them from here as well.
What? That's crazy.
What's wrong?
Was that me? And actually,
Okay.
I totally blacked out there, I guess. I thought it was Angela.
Oh, okay. So the next question says, what's the probability that less than 4? So if it's less than 4, it could be 0 or 1 or 2 or 3, right?
Oh.
So if I were going to do this by hand, I have to calculate 4 things right there. But we have the table. So I'm going to my table.
Are we staying at 20?
Yep, it's still the 20 for my sample. 35 is my probability of success. So I'm looking on my 35 column, my 20. If I want less than 4, so 0, 1, 2, or 3, it should be those 4 numbers. 0.0002, 0.0020, 0.0100. Do you guys see those? Okay. There is, so this table rounds everything to 4 decimal places. If you calculated them all by hand, your answer could be slightly different, like in the last decimals, because you're not rounding as much. So if you are reading from the table, please just write down the numbers you're adding together, so I know that you got them from the table, you didn't just try to plug it all in. So. Alright, and if we add those up, what do we get?
0.1181. Hey, that too has one more decimal place than I thought it did.
And I think on this one, if you'd done it all by hand, you would have gotten 0.0444. So, just if you're reading them from the table, just write down your numbers so I know. What is the probability that at least 4? That means it could be 4 or 5 or 6, all the way up to 20.
Well, can't we take less than 4 and 1 minus less than 4?
Yeah. So we can either add all those, or we could realize, well, at least 4 is the opposite of less than 4. So 1 minus the probability we got on part B. And we get
0.9555.
what is the probability that between 3 and 5? So what can x equal?
4?
Oh, 3, 4, 5. Yeah, sorry, I meant to be including those. So I would go to my table and I need to read my probabilities for 3, 4, and 5. So we get 0.0323, 0.0738, 0.1272. You get 0.233. Is anyone having trouble reading the binomials? I'm going to do one final example today and then just probably give you guys time to work. And that way those of you leaving aren't really missing a whole lot. The formulas for mean and standard deviation from this are pretty simple. Mean is just n times p. N number of trials, p probability of success. Standard deviation is the square root of n times p times 1 minus p. Again, on the formula sheet, we don't have to memorize them, we just have to use them. So if I were doing this scenario, 35% had 3 or more cars, so that's my p. This time I'm looking at a sample of 400. My n is 400. So if I wanted my mean, formula is just n times p. So 400 times 0.35, we get
140. 140.
standard deviation is square root of n times p times 1 minus p. So n is 400, p 0.35, 1 minus 0.35 is 65.
9.5394.
Probably the easiest standard deviation formula we've ever had to deal with. No table required, just straightforward plugging numbers in a calculator. All right. So,
Cross country is dismissed at this time. Cross country is dismissed.
put this assignment up here. So today, just time to finish. If you had questions over yesterday's that you didn't get done, you can start this. Tomorrow or Monday, I'll finish the notes and then I have some time to work in class as well.
I'm so upset that we missed